For a 1200 amp electrical service, the following conductor specifications are recommended. Suitable conductor types include aluminum or copper THHN or XHHW. The recommended conductor size is 750 kcmil. You will need 3 phase conductors, 1 neutral conductor of the same size as the phase conductors, which is also 750 kcmil, and 1 ground conductor with a minimum size of 250 kcmil. There are additional considerations to keep in mind when installing these conductors. Firstly, local electrical codes may have specific requirements for conductor types or sizes, so it is imperative to consult and comply with these local regulations. Secondly, the conductors must be installed within a conduit or raceway that is adequately sized to accommodate all the conductors and ensure sufficient ventilation to prevent overheating. Thirdly, ensure the conduit or raceway is securely supported and properly protected from any potential physical damage that could compromise the conductors. Fourthly, the conductors must be terminated correctly and securely, strictly following the manufacturer's instructions for the specific connectors being used and adhering to all applicable electrical code requirements for terminations. Fifthly, it's crucial to perform regular inspections of the connections and tighten them as needed. This proactive maintenance helps prevent loosening over time, which can lead to overheating and potentially hazardous conditions. Proper conductor selection and installation are critical for a safe and reliable 1200 amp electrical service. Consulting with a qualified electrician is always recommended to ensure compliance with all applicable codes and regulations. Remember to always de-energize the circuit before working on any electrical components and follow proper safety procedures to prevent electrical shock. Different types of conductors have different ampacities. Ampacity refers to the current, measured in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The National Electrical Code, or NEC, provides tables that list the ampacities of various conductors based on their size, insulation type, and installation conditions. These tables are essential for determining the appropriate conductor size for a given load. THHN and XHHW are common insulation types for conductors. THHN stands for thermoplastic high heat resistant nylon coated. It is a widely used general purpose wiring material suitable for dry and damp locations. XHHW stands for cross-linked polyethylene high heat resistant, water resistant. XHHW insulation offers superior moisture resistance compared to THHN and is suitable for both wet and dry locations. When selecting between aluminum and copper conductors, consider the following. Copper has a higher conductivity than aluminum, meaning it can carry more current for a given size. Aluminum is lighter and less expensive than copper, making it a cost-effective option for larger conductors. The ampacity of aluminum conductors is lower than that of copper conductors for the same size, so a larger aluminum conductor is needed to carry the same amount of current. Neutral conductors play a vital role in electrical systems by providing a return path for current from single-phase loads. The size of the neutral conductor is typically determined based on the anticipated load it will carry. In many cases, the NEC permits the neutral conductor to be smaller than the phase conductors for services where the load is primarily nonlinear. However, for a 1200 amp service, it is generally recommended to use a neutral conductor that is the same size as the phase conductors to ensure adequate capacity and minimize voltage drop. Ground conductors provide a path for fault current to return to the source, helping to trip the overcurrent protection device and clear the fault. The size of the ground conductor is determined based on the size of the service entrance conductors. The NEC specifies minimum sizes for ground conductors in Table 250.122. For a 1200 amp service, a minimum ground conductor size of 250 kcmil is typically required. Conduits and raceways serve to protect conductors from physical damage and environmental factors. Common types of conduits include rigid metal conduit, intermediate metal conduit, electrical metallic tubing, and PVC conduit. The size of the conduit or raceway must be large enough to accommodate all the conductors and allow for easy pulling. The NEC specifies the maximum number of conductors permitted in a given size of conduit. Proper ventilation within the conduit or raceway is essential to prevent overheating of the conductors. Overheating can degrade the insulation and reduce the lifespan of the conductors. Securely supporting the conduit or raceway is crucial to prevent sagging or damage. Support should be installed at intervals specified by the NEC and should be appropriate for the type of conduit being used. Terminating conductors properly is essential for ensuring reliable electrical connections. Use connectors that are specifically designed for the type and size of conductor being used. Follow the manufacturer's instructions for installing the connectors. Ensure that the connections are tight and secure to prevent overheating and arcing. Regular inspections of electrical connections are essential for identifying and addressing potential problems before they lead to failures. Look for signs of overheating, such as discoloration or melting of insulation. Check for loose connections and tighten them as needed. Use a torque wrench to ensure that connections are tightened to the proper torque specifications. Working on electrical systems can be dangerous, so it is essential to follow proper safety procedures to prevent electrical shock and other hazards. Always de-energize the circuit before working on any electrical components. Use appropriate personal protective equipment, such as insulated gloves and safety glasses. Follow lockout/tagout procedures to ensure that the circuit remains de-energized while you are working on it. If you are not qualified to work on electrical systems, hire a qualified electrician to do the work. The ampacity of a 750 kc mil copper THHN conductor is typically around 535 amps at 75 degrees Celsius. This ampacity can vary based on the specific installation conditions and the temperature rating of the terminations. Since you need to carry 1200 amps, you will need to use multiple conductors in parallel. To determine the number of parallel conductors required, divide the total current by the ampacity of each conductor. 1200 amps/535 amps equals approximately 2.24. Since you cannot use a fraction of a conductor, you will need to use 3 750 kc mil copper THHN conductors per phase. Similarly, the ampacity of a 750 kc mil aluminum THHN conductor is typically around 475 amps at 75 degrees Celsius. Using the same calculation as above, 1200 amps/475 amps equals approximately 2.53. This means you would need to use 3 750 kc mil aluminum THHN conductors per phase. Keep in mind that these are just examples, and the actual ampacity of the conductors may vary based on the specific installation conditions and the temperature rating of the terminations. Always consult the NEC and a qualified electrician to determine the appropriate conductor size and number of parallel conductors for your specific application. The neutral conductor in a 1200 amp service is typically sized based on the expected neutral load. The NEC allows for a reduced neutral size in some cases, but it is generally recommended to size the neutral conductor the same size as the phase conductors for services of this size. This ensures that the neutral conductor has sufficient capacity to carry any unbalanced current and minimizes voltage drop. For a 1200 amp service with 3 750 kc mil copper THHN conductors per phase, the neutral conductor should also be 3 750 kc mil copper THHN conductors. The equipment grounding conductor, or EG, is used to provide a low impedance path for fault current to return to the source. The size of the EGC is determined based on the size of the overcurrent protection device protecting the circuit. For a 1200 amp service, the EGC must be sized according to NEC Table 250.122. Based on this table, the minimum size of the EGC for a 1200 amp service is 250 kc mil copper. The EGC can be either copper or aluminum. If aluminum is used, it must be sized larger than copper to provide the same level of protection. The EGC must be installed in the same raceway as the phase conductors. The NEC specifies the types of raceways that are permitted for use with electrical conductors. Common types of raceways include rigid metal conduit, intermediate metal conduit, electrical metallic tubing, and PVC conduit. The raceway must be sized appropriately to accommodate all the conductors and provide adequate space for heat dissipation. The NEC provides tables that list the maximum number of conductors that can be installed in a given size of raceway. The raceway must be supported properly to prevent sagging or damage. The NEC specifies the maximum spacing between supports for different types of raceways. Conductors must be derated when they are installed in close proximity to each other or when they are exposed to high ambient temperatures. Derating reduces the ampacity of the conductors to prevent them from overheating. The NEC provides tables that list the derating factors for different installation conditions. It is important to apply the appropriate derating factors to ensure that the conductors are sized correctly. Voltage drop is the reduction in voltage that occurs along a conductor due to its impedance. Excessive voltage drop can cause equipment to malfunction or fail. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To minimize voltage drop, use larger conductors or run conductors over shorter distances. Parallel conductors are multiple conductors that are connected together at both ends to increase the ampacity of a circuit. The NEC permits the use of parallel conductors under certain conditions. When using parallel conductors, all conductors must be the same size, material, and insulation type. The conductors must be installed in the same raceway. The ampacity of the parallel conductors is the sum of the ampacities of the individual conductors. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect electrical circuits from overloads and short circuits. The overcurrent protection device must be sized to protect the smallest conductor in the circuit. The NEC specifies the maximum size of overcurrent protection device that is permitted for different types of conductors. Ground fault protection is used to protect people from electrical shock. Ground fault protection devices such as ground fault circuit interrupters, or GFCIs, and ground fault equipment protection, or GFEP, detect ground faults and interrupt the flow of current. The NEC requires ground fault protection in certain locations such as bathrooms, kitchens, and outdoor areas. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges. Voltage surges can damage sensitive electronic equipment. SPD are typically installed at the service entrance and at branch circuit panels. Harmonics are distortions of the sinusoidal waveform of alternating current. Harmonics can cause problems such as overheating of equipment, increased energy consumption, and interference with communication systems. The NEC recommends measures to mitigate harmonics in electrical systems. Power quality refers to the quality of the electrical power supply to a facility. Poor power quality can cause equipment to malfunction or fail. Common power quality problems include voltage sags, voltage swells, and harmonic distortion. The NEC recommends measures to improve power quality in electrical systems. Energy efficiency is the use of less energy to perform the same task. Energy-efficient electrical systems can save money on energy bills and reduce environmental impact. The NEC recommends measures to improve energy efficiency in electrical systems. Electrical safety is the prevention of electrical hazards. Electrical hazards can cause injury or death. The NEC provides requirements for electrical safety in electrical systems. It is important to follow these requirements to prevent electrical hazards. When working with electrical systems, it is important to have the right tools. Some essential tools include a voltage tester, an ammeter, a wire stripper, a screwdriver, and a wrench. It is also important to have personal protective equipment, such as insulated gloves and safety glasses. Electrical codes are a set of rules that govern the design, installation, and maintenance of electrical systems. Electrical codes are intended to protect people and property from electrical hazards. The NEC is the most widely used electrical code in the United States. Local jurisdictions may also have their own electrical codes. It is important to comply with all applicable electrical codes when working with electrical systems. A qualified electrician is a person who has the knowledge, skills, and experience to safely and effectively work with electrical systems. A qualified electrician has completed an apprenticeship program and has passed a licensing exam. It is important to hire a qualified electrician to perform electrical work. The NEC is updated every 3 years. It is important to stay up to date in the latest changes to the NEC. The NEC is available for purchase from the National Fire Protection Association, or NFPA. There are also many online resources that provide information about the NEC. The proper installation of a 1200 amp service involves careful planning, selection of appropriate materials, and adherence to all applicable codes and standards. Here's a more detailed breakdown. Firstly, planning and design. Before starting any work, develop a detailed plan that includes the location of the service entrance, the routing of the conductors, the size and type of raceway, and the location of all equipment. Consult with the local utility company to determine the service requirements and obtain any necessary permits. Secondly, service entrance location. Choose a location for the service entrance that is easily accessible, protected from damage, and meets the requirements of the NEC and local codes. The service entrance should be located as close as possible to the load center to minimize voltage drop. Thirdly, conductor selection. Select conductors that are of the appropriate size and type for the load. Consider the ampacity of the conductors, the voltage drop, and the environmental conditions. Use conductors that are listed and labeled for the intended use. Fourthly, raceway installation. Install the raceway in accordance with the NEC and local codes. Use the correct type of raceway for the application and ensure that it is properly supported and grounded. Seal the ends of the raceway to prevent moisture from entering. Fifthly, conductor installation. Pull the conductors through the raceway carefully to avoid damaging the insulation. Use a pulling compound to reduce friction. Do not exceed the maximum pulling tension for the conductors. Sixthly, terminations. Terminate the conductors properly at all equipment. Use connectors that are listed and labeled for the intended use. Torque the connections to the manufacturer's specifications. Seventhly, grounding. Ground the service entrance equipment in accordance with the NEC and local codes. Use a grounding electrode system that meets the requirements of the NEC. Connect the grounding electrode conductor to the service equipment and to the grounding electrode system. Eighthly, overcurrent protection. Install overcurrent protection devices that are of the appropriate size and type for the load. Coordinate the overcurrent protection devices to ensure that they trip in the correct sequence. Ninthly, labeling. Label all equipment clearly to identify its function and voltage. Use permanent labels that are resistant to fading and damage. Tenthly, inspection. Inspect the installation carefully to ensure that it meets all applicable codes and standards. Correct any deficiencies before energizing the system. These steps provide a more comprehensive overview of the installation process, emphasizing the importance of careful planning, proper material selection, and adherence to all applicable codes and standards. Remember to consult with a qualified electrician for any electrical work.